Okay, so let's review what the definition of a conjugacy class in a group is. So from your course in abstract algebra, you might remember that if I have a group G, then the conjugacy class of G, of a little g in big G, is the set of all conjugates of G. So I take my G and I range over all other elements of G and I look at H, G, H inverse. Great, so one nice way of thinking about conjugacy classes is that they are exactly the orbits of the conjugacy action of G on itself. So remember, whenever you have a group, there's an action of G on itself that sends, given by G cross G, the map from G cross G to G, that sends H comma G goes to H, G, H inverse. And the conjugacy classes are just exactly the orbits of this action. Oh, and so that means that the conjugacy classes actually partition the group. Because remember, the orbits always partition the set that's being acted on. Here, the group G is the set being acted on. Excellent. Okay, so then the goal of the rest of the video is to understand the conjugacy classes in the symmetric group. Let's begin with a lemma that will lead us to the full classification. So if I have sigma in Sn, so if sigma is a permutation of the numbers 1 through n, and I have a k cycle, so this is another permutation in Sn. Let me write in Sn. Let's do that. I have a k cycle in Sn. So remember, this is the permutation that sends a1 to a2, a2 to a3, all the way up to ak minus 1 to ak, and then sends ak to a1, and doesn't do anything else to any of the other numbers between 1 and n that are not listed here. So if that's a k cycle, then the conjugate of the k cycle by sigma is just another k cycle. It's the k cycle given by sigma of a1 dot sigma of ak. So it's worth pointing out that before, when I said when we write down cycles, we always start with the smallest element of the cycle, and you don't have to do this because you can sort of move the elements around in the cycle cyclically, and the notation still tells you the same permutation, the correct permutation. And so this may not actually be in like sigma of a1 may not be the smallest number here. But you can sort of cyclically move it around so that the smallest number starts at the beginning. Great. Okay. So here's the proof. Let's prove it. So first of all, if I want to show that this permutation is the same as this permutation, I just need to show that they do the same thing on all the numbers between 1 and n. So let's start with a number of the form sigma of ai. Some of the numbers between 1 and n are of the form sigma of ai. It's exactly those numbers in there. So let's start with a number of that form here, and let's apply this permutation to it. Okay, so here's my permutation applied to this number, and well, sigma inverse of sigma of ai is just going to be ai again, because sigma and sigma inverse cancel out. Okay, so now I have this permutation, sigma composed with a1 through ak, applied to the number ai. Great, but we know what this k cycle does to ai. It sends ai to ai plus 1 mod k, Because of course, if i is k, then this will send it back to 1. Yes, excellent. But then I just have sigma of that, sigma of this k cycle applied to ai is just sigma of the k cycle applied to ai, which is ai plus 1 mod k, and this entry is just exactly where that permutation sends sigma of ai, This k cycle sends sigma of ai to sigma of ai plus 1 mod k. Excellent. So what that means is that this permutation, maybe I should say this permutation here and this permutation here do the same thing to any number which appears on this list. Of course, not all the numbers may appear on that list, so now we have to check that these two permutations do the same thing to any number which is not on that list. So, if b is not on that list, well, sigma is a bijection, so that means that sigma inverse of b cannot be equal to any of the ai's on this list, right? If that were true, if sigma inverse of b were equal to one of the AIs, I would just apply sigma to both sides, and I'm going to get that b is equal to sigma of AI. Excellent. Okay, so now let's apply this side to b. So sigma k-cycle sigma inverse applied to b is just sigma k-cycle applied to sigma inverse of b. That part's trivial. But then sigma inverse of b, as we just said, right, for such a b, sigma inverse of b does not appear on this list. It's not one of the AIs. And so the k-cycle, a1 through ak, doesn't do anything to this element. It just fixes that element. And so I can just completely erase the k-cycle, and I just get sigma inverse of b, and of course the sigma and the sigma inverses cancel, and I just get b. Okay, so altogether, what this means is that this permutation and this permutation do the same thing on any number between 1 and n, right? If the number appears on this list, number 1 tells you that they have the same output, and if the number does not appear on this list, number 2 tells us they have the same output. Excellent. Okay, great. So on this board, we're going to start with an example that illustrates the previous lemma. So remember, the previous lemma says, what happens when I take a cycle, a k-cycle, and I conjugate it? So in this case, let's take the 4 cycle, 1, 2, 3, 4, in S6, and let's take the element of S6, sigma, which is in cycle notation 3, 5, and 1, 2, 6. So then sigma inverse, so remember S6 is a group, so every element has an inverse, and sigma inverse is 3, 5, 1, 6, 2. Another way of thinking about it is that this is the inverse of this bijection, right? This is a bijection from the numbers 1 through 6 to the numbers 1 through 6, and this is the inverse of that function. Let's just quickly check that that's actually the inverse. So sigma sends 3 to 5, and sigma inverse sends 5 to 3. Great, so also if I did first do sigma, then do sigma inverse, it would send 3 to 3. Or for example, sigma sends 1 to 2, but then sigma inverse sends 2, wraps back around to 1. So therefore doing for sigma first, and then sigma inverse would send 1 to 1. And you can check for the rest of the numbers, this still holds. Excellent, okay. So now let's compute sigma inverse tau sigma. So how do we do this? Let's compute it in cycle notation. And remember how to compute cycle notation. I open the parentheses and I start with the number 1. And then we want to see, where does sigma inverse tau sigma send 1? So first, sigma inverse sends 1 to 6. Then tau sends 6 to itself, right? Tau just fixes 6. And then sigma sends 6 back to 1. And so sigma inverse tau sigma sends 1 to 1. And just close off the parentheses. That's just a single 1 cycle. All right, now we open another parentheses and see, and start with the next smallest number that's not on this list, which is just 2. Okay, and let's see what happens to 2 under sigma inverse tau sigma. So sigma inverse sends, sigma inverse sends 2 to 1, and then tau sends 1 to 2, and then sigma sends 2 to 6. So this, so altogether, sigma inverse tau sigma sends 2 to 6. Let me make sure that's right. Yes, great. Okay, and then we can just compute the rest. We see where does 6 go. So sigma inverse sends 6 to 2, and then 2 goes to 3 under tau, and then 3 goes to 5 under sigma. So altogether, this sends 6 to 5, and then we can check that the rest of them turn out to be 4. Close the parentheses, and then 3. Okay, and so that, if I ignore the 1 cycles, as we do, this is 2, 6, 5, 4. So it is, again, a 4 cycle, as our lemma said it should be. And let's just make sure, well, this really is, right, this should be sigma of 1, sigma of 2, sigma of 3, sigma of 4. Because remember, the lemma says that if I do sigma inverse tau sigma, then if tau is a 4 cycle, then that's just the same thing as taking this 4 cycle and applying sigma to each of the numbers on the inside of that. And so let's just make sure. So sigma of 1 is 2, great. Sigma of 2 is 6, indeed. Sigma of 3 is 5, yes, and sigma of 4 is 4, because 4 does not appear, so 4 is a single one cycle that we've omitted. Excellent. Okay, great. So in this particular case, our lemma checks out, which makes us maybe slightly more confident that our lemma is actually right, that the proof was actually correct. Okay, so now we have a lemma that tells us not just what happens when I conjugate a cycle, but what happens when I conjugate any permutation in terms of the cycle notation. So if tau in Sn has cycle notation this, so it has L different cycles, and they have length K1, K2, all the way up to KL, and sigma is in Sn. Then if I do this conjugation just like before, then this has cycle notation given by exactly the same formula as before. You just apply the formula to each of the K cycles separately. Excellent. And the proof is not so hard. So is a little acute trick that happens in algebra all the time. So if I do sigma, tau, sigma inverse, well, tau is this product of cycles, and so I just write that product of cycles in there. And then, so whenever I write a product of cycles, that's the same thing as saying if I had each of the cycles separately and I compose them in the symmetric group. And what that means is that I can insert sigma inverse sigma in between each of the cycles. Because sigma inverse sigma is just the identity, and so having nothing there is the same as having the identity there, which is the same thing as having sigma inverse sigma there. Excellent. So I do that in between each of the L cycles, and excellent. And then I just apply the lemma from before. So for this cycle, this is just sigma cycle, sigma inverse, and as we know, that's just applying sigma to each of the numbers inside of the cycle. So here I've done that. And I just do that for each of the cycles that appear here. I've done it for the last one, for the Lth one here. And then I claim that this thing actually is the cycle notation of this permutation. And that happens because the numbers here and the numbers appearing in each of the cycles, all those numbers are distinct because sigma is a bijection, right? I started with the cycle notation for tau, and all of the numbers here are distinct numbers by the definition of cycle notation. And so when I apply sigma to that, because sigma is a bijection, I will get a bunch of distinct numbers again. So then this really is the cycle notation for this, and we're done. That was the formula. Amazing. Okay, so now we can check that again on an example. And so I have almost the same example, except I just changed tau to be the permutation 1, 2, 3, 4, and then 5, 6. So it's no longer a 4 cycle, it's just a product of 2 disjoint cycles. Right? This is its cycle notation. And then we have the same sigma, and let's just apply, let's just make sure that the formula works out. So doing sigma inverse tau sigma, compute it in cycle notation, I need to take 1, and I open the first cycle, and I put a 1 there, and then let's see where that goes. So sigma inverse sends 1 to 6, tau sends 6 to 5, and then sigma sends 5 to 3. So this should have a 3 here. Let me make sure that I'm right. Yes. Okay, and then what about 3? So sigma inverse sends 3 to 5, tau sends 5 to 6, and then sigma sends 6 to 1, and so that means altogether sigma inverse tau sigma sends 3 to 1, so I close the 2 cycle. Great, now I open another cycle. And it turns out, like before, this ends up being 2, 6, 5, 4. I should have said, so let me say first that, remember that the order in which we write the cycles doesn't actually matter. So it looks like something has gone weird because this is a 2 cycle and then a 4 cycle, whereas I started with a 4 cycle and then a 2 cycle, but then the cycle notation doesn't care in which way you arrange them. So this is really the same permutation as 2, 6, 5, 4, 1, 3. Then we can really compare them. So then this really is, we can check this really is sigma of 1, sigma of 2, sigma of 3, sigma of 4. Oops, I need to start more to the left. Right, that really is sigma of 1, sigma of 2, sigma of 3, sigma of 4, close parentheses, sigma of 5, sigma of 6. Excellent. Great, so our formula works. Okay, I just tapped the board to wake up my iPad. This is bad. My brain is broken. Okay, so on the next board, we're going to put together both the lemmas to completely characterize what the conjugacy classes in SN look like. So here's the long-awaited theorem, which is that the conjugacy class of an element tau in Sn is given by the following formula. So the conjugacy class of tau is the set of omega in Sn, so that tau and omega have the same cycle types. So the things that are conjugate to tau in Sn are just exactly the things that have the same cycle type as tau. Very beautiful result, and extremely useful, especially in Coxeter group theory. When we apply our Coxeter group theory to the symmetric group, this will be very helpful. Okay. So here's the proof. So if I want to show that two sets are equal, one way to do this is to show containment in one direction and then containment in the other direction. And so first direction's the easier one because we already did all the work. So let's take something in the conjugacy class. That's such a hard word to say, such a hard phrase to say. In the conjugacy class of tau. And so such a thing looks like sigma tau sigma inverse for some sigma in Sn, but by our lemma, the cycle type of sigma tau sigma inverse is exactly the same as the sigma type as the cycle type of tau. Because remember, I've kind of written it down here, right? If I have sigma tau, I've written it again down here. Sigma tau sigma inverse is just, I take the cycle notation for tau, and I just apply sigma to each of the numbers in that, and I obtain something which is exactly the same cycle type, meaning the cycles have all the same sizes as they started. Excellent. Okay, so that means that this thing, right, if I take something conjugate to tau, it has the same cycle type as tau, and so it's in the right-hand side. Okay, what about the other containment? So now we have to take something in the right-hand side and show that it's in the left-hand side. So let's take omega in Sn, which has the same cycle type as tau. So let's write tau as in cycle notation as this, and omega in cycle notation is this. And because they have the same cycle type, right, that means that these numbers k1, k2, all the way up to kl are the same, right? The sizes of the cycles are the same. And let's just not omit the one cycle. So sometimes we omit them, sometimes we don't. In this proof, let's not omit them. So some of these could just be a single numbers inside of a single cycle. Okay, so let's define sigma from the set of numbers 1 through n to the set of numbers 1 through n by sigma of aij equals bij. So all I'm doing, I'm saying where does sigma send this number? It sends it to that number. Where does sigma send this number? To that number, and just down the line. So since each number between 1 and n appears exactly once on this list, right, the list of all the numbers here, it appears exactly once on that list, and it also appears exactly once on the bottom list, on the B list. B list. Therefore, this definition of sigma, this is, I mean, a priori, this is just a function, but actually that says that this is a bijection, right? So it's actually an element, right? It's a bijection, so it's an element of Sn. And so by the lemma, if I do sigma tau sigma inverse, right? Well, by the lemma, that's just applying, right? Here's the cycle notation for tau, and I just apply sigma to each of the numbers in the cycles, with the parentheses in the same place. But by definition, right, sigma of A11 is just B11, and sigma of A1K1 is just B1K1, etc. And so I just, and that thing is just omega by construction. So what we've shown is if I have some omega, which has the same cycle type as tau, I can define some sigma so that sigma tau sigma inverse is equal to omega. And therefore, omega is a conjugate of tau, and so is in the left-hand side of the equation. And that's the proof. Okay, so let's use an example to understand the proof that we just gave of this theorem. So remember, the theorem says the conjugacy classes of a permutation tau, the conjugacy class of a permutation tau is just exactly the permutations omega, which have the same cycle type as tau. And so let's look at a particular example. So let's have tau be the permutation 1, 2, 3, 4. In cycle notation, 1, 2, 3, 4 is the first cycle, and then 5, 6 is the second cycle. And this is in S6. I should say that maybe. So, remember this was a permutation that we had looked at in a previous example. And so the cycle type of this is 4, 2, because there's a 4 cycle and a 2 cycle. So let's just take some other random permutation which also has cycle type 4, 2. So let's take the permutation 2, 6, 5, 4, and then is the first 4 cycle, and then 1, 3 is the second cycle. And I guess it's not totally random since it's exactly the same one from the previous example. Great. Okay, so the proof, right, according to the theorem, these two elements of S6 should be conjugate to each other. And the proof says, how do I get the element sigma that, I can use to conjugate tau to get omega? I make a new permutation which sends 1 to 2, 2 to 6, 3 to 5, 4 to 4, 5 to 6, 5 to 1, and 6 to 3. Right, I just write out omega in some cycle notation, and then I draw these lines. And so if you sort of use these lines to find the cycle type of sigma, you get the permutation 1, 2, 6, 3, 5 is the first cycle, and then 4 is the second cycle. And you can check that the inverse of this is this permutation. You can also check that, in fact, it is true that sigma inverse tau sigma is omega. Okay, great. So you might notice, however, that in our previous example, tau and omega were conjugate to each other, but they were conjugate via a different element of S6. And that is typical. So this sigma is not going to be unique. In fact, it just depends on how I rearrange how I write down my cycles. Right? Remember, previously we had said that sometimes, to be organized, sometimes you write the cycles starting with the smallest element. But of course, the cycle 1, 3 is the same as the cycle 3, 1, right? I mean, this cycle sends 1 to 3 and 3 to 1, and so does this one. So I can just as easily have written omega as 2, 6, 5, 4 as the first cycle, and then 3, 1 as the second cycle. And then I can create a new element of S6, sigma prime, which in the same exact way, just by drawing arrows downward. And of course, I'm going to get a different element of S6 because I've rearranged these numbers. So right here, 5 goes to 1 and 6 goes to 3, but down here, 5 goes to 3 and 6 goes to 1. So in this case, sigma prime is 1, 2, 6, 3, 5, 4. But it's still true that sigma prime tau sigma prime inverse is omega. And you'll notice that this sigma prime really is the same as the one we had in the previous example.